For the Hyperloop, how would you put people on the train itself? Because the outside's at a lower pressure than the inside of the cabin. So how would you get people onto the train?
That's a great question. So just like an airplane, which has a door, which actually serves as sort of like an airlock, the Hyperloop would also have to have a door which would serve as an airlock. And so we're looking at having two separate doors which serve as the airlock or air dock, but those doors would only be activated and connected when you get into a station. So it would be very similar in size to an airplane door, but it would have a different mechanism in the way that it docked to a station. So inside of the pod would be 1 atmospheric pressure, and then you would pass through that airlock into the station, which also would be at 1 atmospheric pressure. So the people would never see the pressure differential which is in the tube. And so part of our technology demonstration, we didn't demonstrate the air docks or the air locks, but we did demonstrate gate valves which would close and provide that type of sealing.
Great, thank you very much. Can you just say a couple of things about where you are with the, I guess, engineering? If I said, hey, I want one of those, can we start on it next week? Would you be able to say, well, hold on, or you know, let's do it, or it's going to take a bit longer, and what are those challenges?
So we did technology demonstration over the course of 2016 to 2018. It's now we're working on the production level design. And so the biggest challenge actually for a Hyperloop system is that it's a new form of transportation, which means there doesn't exist a regulatory framework to cover it from a standards perspective. So in many cases, we can pull from rail, we can pull from aviation, but there are places where those standards don't exist. So we have to basically come up with a design which is compliant with rail and aviation standards where applicable, which is what we're working on now. And for places where there is no standard, we actually have to come up with that standard and work that through. So that process is going to take us about another 2 to 3 years. The first planned project implementation is in India and a route between Mumbai and Pune. And so we're looking at that being operational in the mid to late 2020s. But I would say, yeah, in terms of what needs to be done, we did proof of concept, principle, demonstration of the technologies, but you still have to take it to the production level. And the production level, in this case, has the challenge associated with it that there is no standard for a Hyperloop, and so we're actually actively working on that right now. And we do have an international standards working group, which has people from Europe and the UK that's part of that activity.
Thank you, a very interesting talk. I'm quite interested in sort of counterfactual history. Do you think if people had believed Lord Kelvin, who was a great scientist, but he wasn't very good at some predictions, that this concept would have been implemented perhaps sooner because electromagnetics was sort of understood, I suppose, and general concept. Do you think we would have gone down this route?
So my perspective, my whole background is in the space program. So I've worked with vacuum technologies for most of my career. And so my background was in ion propulsions, which you can only test in vacuum chambers. So the Hyperloop is actually a compilation of technologies which already exist, right? It's actually putting together in a sort of system sense. So vacuum chambers exist, pumps exist. Our vacuum level is not even that low, so it's relatively easy to get to. Pressurized cabins exist, airlocks exist. So it's actually a question of putting them together. So I would say it's more about the political will and the funding to be able to facilitate this and the need based off of existing transportation systems being at capacity than anything else. That's kind of, I would say, which probably has held it up to that point, with one exception. The one exception is that because we're operating at such fast speeds, you have to have autonomous operation. The autonomy definitely has only come in the past decade or so. So we probably couldn't have had it 10 to 15 years ago because of the absence of that autonomy. You can't have a person in the loop for the speeds that we're talking about because you have to be able to decelerate, not at a high rate, but you have to decelerate at a moment's notice once you detect, if there's a problem with the pod in front of you, you need to know when it's having a problem so you can immediately slow down. So I think it's the autonomy that's being developed for the automotive sector, right, and being validated by that, for example, which probably is the biggest technology shift and also cultural shift towards people and actually wanting to see that. That being said, autonomous people movers in airports have existed for years and people have no problem using them. It's just a different way of thinking to not have a person operating a vehicle. And whenever you operate, do an operational certification on a train route, you can do something at the very beginning that you would shift to later on, which would be slightly different. So I would say now is the right time for it because of where we are with autonomy, but the key technologies for a Hyperloop have existed for many years in a different form, and now we're putting them together.
Could we get a question from the gallery there?
Yeah, hi. Anita, very great talk. Quick question about HS2. we're spending £70 billion to take trains up to Manchester. One of the big problems there, I hear, is actually the speed of the trains going through tunnels and the friction caused. Why is this technology, which is clearly available, not being considered for HS2, which the due date is 2040?
I don't know the answer to that question because I don't live here, but I would say that our goal is to be as interoperable with other modes of transportation as possible, so there's no reason why you couldn't take a Hyperloop and then connect up going through a portal, walking over to that station with HS2, but I think all modes of new transportation and mass transit are great. I mean, I only recently was up visiting my mom in Liverpool, and I took the train, the Northern Line train. It was completely at capacity. So the idea of having anything which improves upon that to address the being at capacity, I think is a great thing. So I feel as though, I personally think that evolutionary technology, evolutionary implementations of mass transportation solutions is a great thing regardless. So I would be happy to have any improvement over what we currently have in Los Angeles, for example, which is not much.
And just to piggyback on that, I mean, what is the cost per kilometre, you know, for this sort of system?
So our goal is to be basically, you know, the same or less than any other form of rail transit.
Thank you for the talk. Isn't it counterproductive that you only have 20 people? Why can't you add several pods to make a longer train or pod?
So that's a good point. So the one thing I didn't say is that our architecture is to operate smaller pods, but operate them in caravans. So if you have high demand because you're at rush hour, you'd have many 20-person pods, so you'd be like a longer train. But if it's in the middle of the night and only 20 people need to go from this stop to that stop, then you'd only run pod. So one of the operational costs for rail systems is that sometimes they're not at capacity, right, at off-peak hours, and you have all these things that you don't need connected to them. So this is a way where you can actually match up the number of pods with the number of people who want to go from destination A to B. But what's good about this one is that you can go to destination A to B, A to C, and everybody in that pod is going to the same destination as you. So we solve that by simply caravanning the pods, but instead of physically hooking them together, they're basically just very closely coupled, and then because of autonomy, they're within line of sight of each other, and they know exactly where the pod is in relation to them to maintain that convoy, as it were. But good point.
And the gentleman behind you there?
Thanks. In terms of the thermal environment, which you touched on, and safety and cost, why is a tube preferable to a tunnel?
So you have to be able to maintain a hermetic seal. So with a tunnel for traditional tunneling applications for metro systems, they don't have to be hermetically sealed, right? Whereas this system has to be able to maintain that pressure. So that tube is the reason why you have it. The nice thing about, though, the fact that you have a tube is that if you do have to tunnel, because you have to go subterranean, you have to go through the side of a mountain, the tubes that you normally have to build, you should know about this more than I do, that you have to build for that because of the pressure effects or the dynamic pressure that you get going through high speed in this constrained space, you actually have to make a much bigger tunnel, much thicker walls, because here all of the pressure is contained within an existing tube. The tunneling is actually lower cost, going to be a smaller diameter. But the whole reason for the metallic structure or whatever structure we end up going with is so that you can maintain that pressure. And so it's basically a depressurized vessel, and so it has to have a certain strength to be able to maintain the delta P, which is 1 atmosphere on the outside and 0 atmosphere almost on the inside. So it's just a structural solution.
Another question for the gallery there?
Hi, yeah, thank you. Just trying to understand, what are the constraints in terms of turning and elevations compared to existing travel?
So this is interesting. So one of the difficulties associated with going up a grade for a traditional rail-based system, I don't know where the gentleman is who asked the question, sorry. Oh, there, okay. Sorry. One of the challenges with existing rail-based systems for going up a grade is at speed is that it actually is a lot higher energy cost. So here we're able to do it at similar grades, I would say, to any other rail-based system, and our energy cost is a lot lower because we're not pushing against drag, aerodynamic drag. So that's still possible. And then the other question was related to... Oh, cornering. So radius of curvature is another one. So for this one, because our pods are so small and we use a very specific banking mechanism, we're actually able to take a much tighter radius of curvature than a high-speed rail train would do, for example. So we're a little bit better in that sense, which means that you can occupy less space, tighter turns, which gives you a less expensive land purchase for a given route alignment.
And another one up in the gallery there?
Thank you, and really interesting talk. How do you maintain the pressurized tube if we can imagine traveling from LA to San Francisco? does that mean you only have one pod? How do you envision other pods joining in and maintaining the pressurized environment?
So the depressurized environment is always depressurized. You would only bring it up to pressure if you had to do some kind of maintenance or repair. And so the way you handle that is that every pod that goes into a station connects through an airlock. And because of that, the pod is 1 atmosphere inside of it. It's going through an airlock to a 1 atmosphere station, but the tube that connects to it is always still under that depressurized condition. And so there's a certain amount of energy that it takes to operate pumps to pump the system down to the 0.1% of atmospheric pressure. There's also an amount of energy that it takes to maintain that pressure, but the amount of energy that it takes to maintain that pressure is actually quite low. So it really depends on how leaky your tubes are. And so our tube that we demonstrated out in the desert, for example, can stay that way for months at a time, barely requiring any energy to keep it at lower pressure.
To join in the trip, basically. So, I mean, obviously they're going to have to get on, and you're going to have to open it up. So doesn't that depressurize the whole tube?
It doesn't need to. So basically, if you have to take the pod out for maintenance or repair, if it's just simply going around the system and being used, it always stays in that depressurized environment. If it has to be taken out for repair, we have a gate valve technology that you close, and then you only open up that section, which is at atmospheric pressure. So if you needed to take one out, you put it into a section, you close the gate valves, you bring up that section to 1 atmosphere, and then you remove the pod. But the rest of the system is still depressurized. And so that's a technology that we also demonstrated. So basically how we did that was that we only had a unidirectional system. So when we pulled it out, we had a vehicle which was sitting in a 1 atmospheric section, which we then pumped down by closing the valves, sent it out, brought it back. And so that's relatively easy to do.
Hi. In the original Hyperloop paper, they had a gas turbine at the front for gas bypass around the front of the train, and you've left out that complexity. You've used magnetic levitation rather than air skids. Did that mean that you had to have a bigger diameter of cylinder to let the air around the vehicle?
Oh, so you're referring to aerodynamic blockage. So aerodynamic blockage ratio, it adds a level of inefficiency because you now have to deal with that aerodynamic force, but it's actually relatively benign because the pressure is so low to begin with. So if you're in a traditional wind tunnel and you blocked out the entire wind tunnel, then you're driven up by this 1/2 rho v squared. I'm sorry, there you are. Sorry. So because the pressure is so low, that dynamic pressure increase because of it is almost insignificant. So it has no problem. And so, we actually choose the blockage ratio to be just the most efficient to combat that increased aerodynamic drag that you get because of the blockage, but it actually represents a very small portion of the overall energy consumption. And so, I know maybe you're referring to like the SpaceX competition where they used the air bearing system. So yeah, we don't have any connection to that. We're a totally separate company, a totally different technology, but it allows you to be incredibly energy efficient if you can operate off electricity. Just if you do the trade.
Sorry, I think there was a question behind you as well there.
If Hyperloop has to go around corners or over hills, what maximum G-forces do you expect to impose upon passengers?
So we treat the maximum G-force on the passengers as a design constraint. So in any scenario, we will never allow the passengers to experience more than 1/4 G, which means that you would choose a gradient and you would choose a radius of curvature so that you will always stay within that maximum deceleration. And that's based off of passenger comfort limits from studies which have been done to find out like what makes people feel uncomfortable, what makes people feel ill. So the 1/4 G limit is actually the limit that if as long as you stay at 1/4 G or less, you don't even have to wear a seatbelt. So that's where that comes from. So aircraft, for example, you can experience 0.6 G routinely during acceleration and deceleration. If you fly a small airplane, fly a small airplane. If you bank, you can experience 1.5 G. So 1/4 G is basically well within the limits of what any range of passenger would feel comfortable with. The one thing that makes people feel ill actually is what they call jerks. So basically like, a time derivative in acceleration when you're like bouncing around like that. That's what makes people feel sick more than anything else. And in a Hyperloop system, you never get that because there's no chance for bouncing around. There's only levitation and then moving forward and then acceleration, deceleration. And if you bank, then you'll also feel some acceleration in a horizontal sense.
I think there was another one just behind you again there.
Hi there. I'm fascinated or intrigued that the first application of this is passenger transport. I just wondered if or has any consideration been given at the start of this to freight transportation? What were the different constraints there?
So it is by definition compatible with either being for passenger or cargo, and there is interest to have it as cargo transport for high value cargo, but because we're trying to create a single product, because if you're limited in money, you can't do everything, so we're creating a smaller vehicle which is compatible with like a basically palletized cargo for high value freight like Amazon might want to use or something like that, so it certainly could, and from a safety case perspective, you could easily use a route which is built up to start transiting cargo in before you send people on there, before you get your full operational certification. So there's nothing to prevent this from carrying cargo, and cargo obviously has a much lower sensitivity to passenger comfort and things like that than people would. So it inherently can carry high value cargo, and the way you can think about that in an architectural sense is that for a given line, you're using it for people during rush hour, but during non-rush hour, you would then have pods moving cargo around. During the middle of the night, you would have pods moving cargo around, but only high value cargo. Like we're not going to be able to pick up the big containers that you would get at like the full container that you would get out at a port for boats. But you could have within those containers pallets which could fit within these vehicles.
Likely that we'll see freight being the first use case, or will they both happen together?
That I don't know, but we did have a press release probably out a couple of months ago, which was cargo speed, which was for the use of cargo with DP World, I believe. So, but either one, that line, whatever line you pick, could be used for cargo or for people, and it's compatible with both.
We have the next question from the gallery there.
Yes, hello. The Hyperloop looks really interesting, and it's a great point-to-point solution, but it seems piecewise point-to-point, or piecewise point-to-point, kind of like a trunk line on a telephone. And a big innovation on the internet was packet-switched networks. Also with transportation, where you have standardized containers that are routed onto trucks or ships or what have you. Have you considered kind of packet integration with Hyperloop into cities and maybe even into packetized elevators, things like that, to have a complete integration?
I'm not familiar with the terminology they use in terms of packetized, but I think maybe the one way I could answer your question is that our architecture is that you basically have a main line going in each direction, and so pods will enter that main line at the nominal peak speed for that main line, which means that if you want to depart to go to another destination to pick up, to either drop off your passengers and pick up passengers, you can do A to B, A to C, A to D, and you never have to stop and start. So in that sense, when you get to that location, let's say point B, you can then connect with other pods there for people who want to go on to C, for example. So it's maybe similar to what you're saying, but not completely, because I'm not familiar with your language, but you can certainly send me a message afterwards, and then I could see how we might be able to integrate that.
Sure, each pod seems like a packet. If you can route that through the whole network, that's great. And if you can exchange that packet or pod onto other networks as well, like the packets you were talking about.
Oh, so I think that's true. So I think, in the initial implementation, we're probably going to look at like a point A to point B to point C and just 3 networks. We're designing it to be scalable to about 8 networks. But it's true that if you want it scalable to an entire landmass, there may be something about this architecture which isn't compatible with that. But that's probably like 50 years out as opposed to the next 10 to 15 years. So for the very first product, it's important for us to focus on something that we can operate and solve a particular country's transportation needs. But certainly if we can come up with ways to put that aspect into the architecture, we would like to.
If the Hyperloop is going to be traveling at 1,000 kilometers per hour, and the maximum acceleration is only a quarter G, how long would be the stopping distance, or wouldn't that be very inefficient? Because only a quarter G, if it's traveling that quickly, it would have to have a very large stopping distance.
It's true, and so, but that is driven by passenger comfort reasons, right? The only way around that is to have a higher deceleration rate, but people wouldn't feel comfortable with it. So the cost associated with having to have these on-ramps and off-ramps to meet getting up to peak speed is certainly, there's a cost associated with that. So that's the reason why you wouldn't use it for a metro system, because you would never ever get up to peak speed, right? It would be pointless. You don't get the benefit of this higher speed. So it's only good for a system which is, 40 kilometers plus up to about 1,000 kilometers. So it's just because you have to facilitate a whole range of people who might ride your system, and so going with a 0.6 G acceleration profile just isn't comfortable for everybody, and so there's nothing you can do about that, unfortunately.
And linking on to the previous question, do you think that a Hyperloop, for example, built by another company like SpaceX, do you think they're going to be compatible, so in the future, in 50 years, in a Hyperloop built in like South America, you can put one of Virgin's pods into the actual tube and it'll be compatible, or will there be different tubes, different sizes, so the pods won't be compatible?
So that's a really good question. So I think that's where, a universal interface comes in, and is that the right thing to do for society? Is that the right thing to do for a certain group of countries or for a group of companies? And I think the debate is still out on that one. But that being said, once you've defined the interface, in this case the interface would be the tube, would be the power system that you're connecting to, would be the inner diameter of that tube, then as long as you designed a vehicle which was compatible with that interface, then it would work. So analogy to that would be launch vehicles. So a launch vehicle is a platform that launch a spacecraft. There's a known interface that you have to bolt onto if that launch vehicle. There's a known set of environmental requirements that you have to work to. As long as you can fit to that interface, you can have your system and come in there. So, but it's not like everybody who builds a spacecraft isn't going to be like, well, I want to build my own launch vehicle to launch my own spacecraft. You don't have to, right? You can be compatible with what already exists. So there are times where you have to choose the level at which you define the interface, and then everyone has to be compatible with. And because this is a new mode of transportation, that very much is an open debate as to how one would do that.
And the lady behind you there?
Hi, very interesting talk, by the way. I just wanted to find out if you're having like a Hyperloop in a developing country, what is the cost associated with that? Because you can easily swap out Virgin trains going from London to Glasgow and go from point A to point B really easily, and that would work very well in a country like this that's quite developed. But if you're looking for like developed countries that probably have like someone like Mumbai or Lagos that have like a lot of people, how would that be to kind of manage the cost? Would it be something that people could afford, or would it be something that would have to work here first before it could go to like a developing country?
So that's a really good question. And rail systems and aircraft travel exist all over the world. Rail typically is a lot cheaper. So the cost of implementing something has the initial capital expenditure. The initial capital expenditure for an infrastructure project is largely related to human labor to put in columns, to make bridges, and to lay whatever it is that you're laying. And so when you have it in a country where the cost of labor is a lot lower, then that cost of the implementation actually comes down. So in that sense, it's somewhat proportional. Then you get to the operational cost. And so there you have to set a ticket price that people can afford based off of their income levels, but you also have to set a ticket price that whoever is the operator is going to make money from. Inherent to this system is a much lower operational cost because your energy consumption is a lot lower. The wear and tear on the vehicles and the track is almost zero. And there's no drivers in the system, so you actually come back with a very low operational cost, which then translates into a pretty big saving for the end user. So there really shouldn't be a difference in the ticket price for a rail system for, let's say, an Indian Hyperloop versus an Indian railway. And we already know that from our initial studies that we've done for our previous feasibility study in India. The capital expenditure is always going to be there for any country, and they have to be willing to spend the amount of money as it takes to implement, like the Crossrail in London, for example. And as long as they're willing to do that because they've decided it's something that their society needs, and that gets covered, then you're just left with the operational cost, and this is a way to actually reduce the operational cost.
We're living in a nastier and nastier world with lots of terrorism and so on. Has any thought been given to the risks, security risks associated with this technology?
Yes, and so there are standards which exist that govern cybersecurity. So for air traffic control for airplanes, right, there's a chance for cybersecurity. For anybody who's going to have any kind of autonomous system, there's the chance for cybersecurity. So there's a set of standards that you have to work to show that your software system is robust and safe against that. With regards to physical security, there are requirements basically on what are your potential scenarios, right? Could somebody drive a truck into it? So you can choose to either use a barrier mechanism, you could choose to make your structure strong enough to handle it, or you could choose to have some other type of control. So there are standards that you have to comply with. Your design implementation of how you show you've mitigated that scenario is kind of up to your technology, up to your company, but we're looking at all of those things. And so the best analogy I would say here would be like a pipeline, for example, or a rail system. But because we have an elevated construction, a lot of the issues where something can drive right into the track, for example, can't happen because it's already elevated construction. So that facilitates some of those safety scenarios.
Just a very long vacuum tube seems to be incredibly fragile and vulnerable.
So, I mean, having a pressurized having a pressurized vessel over large distances has been done before, right? That exists for oil pipelines and natural gas pipelines. And those actually have the potential to have combustibility associated with them. So those are far dangerous in that sense in terms of the final product that could happen to the environment. But in terms of the structural integrity, it's a delta pressure scenario. So you're designing to a delta pressure. So here you're depressurized instead of pressurized. But you can choose to design your structure such that you accommodate whatever the nominal load is and the off-nominal load is. But you can also choose to have barriers instead of putting that all on the structure.
Thank you. I seem to remember, must have been about 10 years ago, reading a paper on the possibility of a Hyperloop across the Atlantic. And one of the things they came to the conclusion was that to build that, it would have taken the entire world's output of steel for about 15 years just to build the tube. And the other thing was, they said, well, how do you ensure that the pod never touches the wall of the tube? Because if it does, you've got about 5 ways to die within seconds. And, just the kinetic energy would kill you, the friction would kill you with the heat, the tube would rupture, you'd lose your air, so you'd stop breathing, and then you get seawater into it. So, that was, it really killed the concept of transatlantic, and that's why I perhaps say you said it wasn't a possibility.
Oh, so this implementation is definitely not planned to be over water bodies at all. It's definitely planning to be, routes between large urban centers in one state to another state, or perhaps one country to another country. So I would say I don't have a design solution today which addresses like how you would travel over the water. I think that'd be very difficult because, the ground by definition isn't stable because there's waves moving and things like that. In terms of the amount of steel that it takes to create a 140-kilometer line or a 700-kilometer line, that's something we can calculate really relatively easily. Yeah. So then there is enough steel being produced there. We're actually working directly with steel manufacturers and steel producers to figure out how that would affect their pipeline. That being said, if everyone decided to build Hyperloops in their country now, right, the next day, all of a sudden that probably would drive up the price of steel, right? There'd be an enormous demand, and there's probably a lot of places which would be happy about that. But usually these things don't all happen at the same time. It happens one place, then it happens another place. But we are very much in contact with many of the steel providers and concrete providers, for example, and they're all interested in working with us, and it doesn't seem like an impossibility. And so I think your other question was about water getting into the tube. So we're not planning on having anything which is floating on the water. There may be places because of a route alignment where you have to go over a lake or a river. There you would have to have a bridge, which is elevated construction. If the municipality wanted it, like in New York, for example, and they wanted to have a subterranean tunnel that goes beneath the Hudson, then you would follow the same design principles as you would for a metro system that went subterranean beneath the water. Oh, it's pod touching the wall. So there are certain functions that have to have a reliability associated with them. And one of them is the control authority, right? Such that you can't actually go off the track. So you have to have a sufficient control authority in your magnetic system to prevent that from happening. Yes, and we already demonstrated that. So, and so then you're designing against, track tolerances. You're designing against seismic activity, and then you're designing against power failures to be able to capture that. But you have to design that level of reliability and robustness into the magnetic control authority to prevent that from happening. And in the event that you reach a scenario where, let's say you lose power, you would decelerate and you would slow down, right? But even that, because of the magnetic force is strong enough that you actually won't go off because of that. But you can actually design the system to prevent those sorts of things from happening, having enough control authority.
The gentleman up here in the blue shirt there.
Thank you very much. Continuing slightly on the same theme, how do you plan to evacuate passengers in the event of a catastrophe? I mean, a serious seismic activity or something that is beyond design expectations? So
there are several different use case scenarios for off-nominal operations. A simple one would be that you simply, let's say something's not performing properly, you have a backup power supply system, and you move yourself along to the next station, and you just exit the next station, right? That's one example of what you do. The probably worst case scenario station, which is that you can't move, you actually close the gate valves for that segment, you repressurize that segment, and you exit through an emergency exit hatch.
You talked about having your pods come in caravans when you had a lot of activity. Does that mean that you'd have sidings in the vacuum domain where pods would be situated where they weren't in use?
Yes, you actually have places where they'd be stabled when they're not in use, and they would come into use and enter the system when needed to be able to support a longer caravan.
And that would be in the vacuum domain?
Yes, it would be in the vacuum domain.
Okay.
I mean, at the same time, if it didn't make sense because that occupied too much space, then you wouldn't. But we were making a certain assumption of how many maximum number that we would need for a given route alignment, and then that's the number that would be in the vacuum domain. That doesn't mean ones can't come out for servicing or maintenance, for example, and they would have to go back in again.
And what kind of utilization of the tube do you expect? Could the tube be full of pods in a massive caravan, or is there necessarily a larger distance between them?
So we are setting a maximum number, which there are certain things that I can't, give you all the numbers and the details, but we are setting a certain maximum number of pods in a caravan, so it's not going to be like 100. It'll be probably about 15 or less. Hi, it seems to me the audience is quite good at envisaging risks in this. Okay, so we're all from very diverse backgrounds, but there's 300 of you. How do you envisage the risks without succumbing to some sort of groupthink and missing out? Because this is the intellectual firepower that's all deployed here, right? You've got lots of intellectual firepower, but you may well succumb to thinking about the problems in very narrow ways. Oh, so the way you do it from a rail perspective and the way we did it from the space program perspective is that you actually have to do thought experiments looking at off-nominal scenarios of what can go wrong, and you actually create fault trees of what could go wrong in terms of these sort of peopled operation systems. You have to do the same exact thing on the hardware side, so you can think of them as like people fault trees versus hardware fault trees, and so we go through that process. But part of being approved by any regulator is to actually have that taken a look at by independent safety auditors, and they actually take a look at what you do too. So we do engage many people. So we have a group of international experts in rail and aviation who we work with as well on that front.
How are the pods powered? Are they battery powered, or is there an electric kind of thing, rail?
So there is an electric rail and there's also battery. So there's primary power on the electric rail and then tertiary power on the batteries. And then you can also recharge the batteries at stations.
Okay.
Thanks.
Question over here, thanks.
Hi, you mentioned about the political will as being one of the obstacles to implementation, and it strikes me that it's an ideally suited system to Nevada where there are no people, because it's beautiful on the inside, but it's large, obtrusive, and it's spectacularly ugly from the outside, and it's pretty much inconceivable that something like that could be driven into the heart of London, given the kind of London property prices and the power of the people versus the power of government at the moment. It's not like the 1960s. So is it even conceivable that this could happen in Washington or New York or Boston? Or are places like India more likely for at least the decades to come?
So I mean, that's a tough one for me to know the answer to, because I've never myself, talked to a government official and said, do you think this is ugly and do you want to put it into your state? The interesting thing is we've had many government officials come to us saying we're super interested at implementing this route in our domain. So we have many different engineering feasibility studies underway in the United States, Colorado, a network which goes between many of their major cities and the tourist locations out to Vail and Colorado and things like that. We have Missouri interested in a route between Kansas City and St. Louis. We have Texas interested in a route. We have the Mid-Ohio region interested in a route. So the governments actually are interested, and they're coming to us saying that we want to implement this thing, knowing the fact that nominally, if you want to have it at low cost as possible, you'd want to have this above ground implementation. So I think it is true that there's going to be individual homeowners in certain locations who think this looks ugly, and that debate will always happen. And that probably has to go through whatever system that happens to me. Like where I live in Los Angeles, whenever a new train line gets put in, it's always put in above ground, and there's, people debate it, and people say, I don't like it in my backyard, and there has to be a back and forth between that. So I assume that will always have to happen for any mass transportation system. That being said, in an urban area, you can have it subterranean, it just costs you more to do it, right? So, and there's a cost to that too, right? Take a look at London right now. There's all kinds of public works going on because of all the stuff that's going on under the ground. So I think that's a decision that a society has to make to be, more green. But it's not like freeways are beautiful, right? It's not like the noise from freeways is beautiful. It's not like polluted air is a beautiful thing. So there are trade-offs that governments and societies have to think about, because if you can solve your air pollution problem by having this, all of a sudden your quality of life does get better.
And one in front of you there, if you could pass the mic down.
Thank you. How many countries are you hoping to implant the Hyperloop in?
So it's pretty much anybody who would like to implement this. We would love to work with them to implement it in their country. But right now we're looking at India, a route between Mumbai and Pune, several locations in the United States, and then also in the Middle Eastern region. So for places that do not yet have mass transportation infrastructure, this is a wonderful new technology option that they can implement. For places who have a mass transportation infrastructure but is already at capacity, this is a way to solve that capacity problem. So pretty much it could be implemented anywhere over a range of terrains and environmental conditions because you are creating your own microclimate. And then something which I think is interesting is that in a place like the Middle East where the environment is very difficult, right, having a microclimate that you're creating and maintaining for your mass transportation system is actually quite desirable.
All right, one up in the gallery there.
Why is the maximum speed at 1,000 kilometers per hour?
So we have to so we want it to be faster than air travel, right? Because the faster you are, the more capacity that you can push. But we also wanted to pick something which was reasonable for route lengths from 50 kilometers to 1,000 kilometers. So we're trying to design a system that can handle both of those ranges. And so if we picked something which was too high, then we were over-designing the system for our first set of implementations. So it's not to say that we couldn't in the future, if people wanted to implement, 1,000 to 2,000 kilometer routes, go to a higher speed, we could probably do that. There's actually nothing to prevent you from continuing to accelerate to get to those faster speeds. But for the route lengths that we're looking at now, the best, most efficient use of money and energy is to just take you up to the maximum of 1,000 kilometers per hour.
Further than 1,000 kilometers per hour, will it affect the people inside the pod?
Not as long as you don't increase the acceleration beyond the quarter G. So your body only feels a force if you're accelerating. It doesn't care what your velocity is. So if you still accelerate at the quarter G, your body still feels that force, but you would just accelerate for a longer period of time, get to a higher speed, and then coast like a spacecraft does. And for you, you don't feel anything when you're operating at a speed as opposed to accelerating. So you wouldn't care. But similarly, you would have to have a longer braking distance to decelerate at the quarter G.
So when I came here today, I turned up to the tube station, tapped my oyster, and then there's a tube within 2 minutes. With the pods, is that the kind of departure rate we'll be looking at, or do you need to book a ticket well in advance?
We are we are looking at given you'll have to wait a couple of years before you get to the first one. But we are looking at an on-demand site system, so where you would have an app. We've already developed the app actually, so where you would be able to call, I want to go to destination B, and then you probably have to wait somewhere between 2 to 4 minutes as well. It's going to depend upon how many pods that we have in the system, but based off of the network modeling that we've done for a given route, for example, in India, we anticipate no longer than a 4-minute wait time. And the tube is great in that sense. I've been taking it all week.
With security, so with airports, one of the biggest problems, or the most annoying thing sometimes, is turning up and waiting for hours to go through security. Do you get that here with Virgin Hyperloop One or not?
So where the regulation for airport security comes in is related to aircraft. So it isn't actually imposed on rail in the United States, and I don't think it's imposed on rail here in this country. So there is no current government mandate which would require a ground-based transportation system to have like that type of security interface. That being said, airport security interface is not very high-tech at all. There are so many other ways you could do security interfaces, which basically use the facial recognition, walking down a tube, right, where they really verify that you are who you are. So there's no reason why you have to go with an airport-type security system to provide a safe travel experience for passengers. So part of our company is developing software, and we are going to come up with a more efficient, high-tech solution for dealing with security, which uses facial recognition as opposed to the traditional I walk up to a gate and wait for an hour in a line, because there's no reason for that. That's only mandated by airports because that's how airports are set up. And then the other thing, which I don't think I mentioned here, is that because this is more like a metro, the stations are going to be centrally located. So with an airport, you got to go an hour to be able to get to where you pick up your airplane. Here, it's going to drop you off in the city center and then interoperable with other modes of transportation, whether that's high-speed rail, Virgin trains, or the tube.
Hi, I was going to ask, has present-day technology been a barrier to some of your ideas? Like you'd have something, but then due to technology, you're just not far enough or anything like that? Has that presented any barriers in slowing down some of the sort of backlog of ideas in any way?
I would say to date, no. Actually, so that's why what I found so interesting about this problem is that the technologies already did exist, it just hadn't been pieced together yet. So there's nothing about pumping technology, there's nothing about the vacuum structure, how to design that, there's nothing about the composite or whatever vehicle choice you choose for a fuselage. The one place where maybe there isn't a commercial analog would be an air dock, for example, right? An airplane door is slightly different than an automated air dock, but that isn't a technology barrier, it just means it's an engineering development to get you there. So I would say at this point there's nothing that presents itself from that perspective. The biggest challenge, I still do believe, and it falls within the bailiwick of the organization that I manage, is the fact that there isn't, it's a new mode of transportation, which means there isn't an existing regulatory framework for a new mode of transportation. I think that probably has the most uncertainty and challenge associated with it, but the way we're battling that is head on, which is by pulling from standards from aviation, metro, rail, and then working really early on to identify places where those standards don't exist. For example, power electronics in a partial vacuum environment, the only place that exists on Mars. So there are no standards from Mars, and NASA doesn't really represent a standards agency, right? It represents like a government agency. So those are the places where I think the largest challenges lie, is making sure that the design is compatible with an unknown regulatory framework, and we're doing everything we can ahead of time to address that.
I think that's all we've got time for tonight. So would you join me in showing Anita our thanks in the usual way?
Thank you.